Flux-Pinning to Modular Spacecraft. And he presented this subject at the GNC conference last year, and also he has a technical note he will be on this topic. Please, Robert.
Thank you. So I fully understand that here we are at the end of the end of the morning on the last day of the conference, and Hawaii is out there. So when I say thank you for coming, I really mean it. What I can show you is me getting very excited about these Flux-Pinned interfaces things that we're researching. What these are devices that exploit actuated distance effects between magnets and superconductors with applications to the assembly and reconfiguration and actuation of modular space systems. Now, on the one hand, this is sort of a device to actuate a formation flight mission. On the other hand, it's also sort of an enabling technology for non-contacting assembly of space missions. And it's this latter view that I favor because the Flux-Pinned interface provides a stiffness and damping force between spacecraft modules. So why are we doing this? In a nutshell, building big things in space is really hard. It's difficult. We have to build really expensive hardware. We have to deal with a very harsh environment. We require very reliable systems, and if we want to build anything of any really large size, we need to either pack it very efficiently and deploy it cleverly, or we need to fractionate a system into subcomponents that can be assembled on orbit. This is just because of fitting things in launch vehicles. And it's risky. There are hazards to both the physical hardware that we put up there and the astronauts who may be assembling things. This is an image of astronaut Scott Krasinski repairing a tear on an ISS solar wing. And when this happened, I remember one news agency calling this the most dangerous spacewalk ever attempted. So while we can build big things in space, new technologies might be helpful. And what we want to do is take this physical interaction of magnetic flux pinning and build interfaces that can provide passively stable interactions between spacecraft components that will be robust to some or all failures in software and power between components, and allow us to repair, replace, extend, reconfigure modular systems. Now, it's important to give a little bit of point out that there are some related sort of action at a distance technologies for assembling large-scale systems or formation flight. For particularly electromagnetic and Coulomb formation flight, such as Dave Miller's work at MIT and Dr. Schaub's work in Colorado. Now, this slide looks very sort of compare and contrasty, but I want to make the important note that we don't see ourselves as competing with these technologies, but rather as complementing them. And the reason is that they work better in different situations, excuse me, and offer better effects. EMFF and Coulomb formation flight can get you very large range separations between elements of the formation flight structure. Flux pinning gives you very small ranges, but with the added benefits of passive stability, you don't necessarily need power to maintain it, and the potential of limited environmental interactions with ambient magnetic fields or between spacecraft. And I'm skimming through this here, but if you want specific details, you can ask me at the end of the presentation. So magnetic flux pinning, what is this thing I'm talking about? It's an interaction between magnets and superconductors. If you're familiar with superconducting physics at all, you might be familiar with the Meissner effect, where a superconductor repels a magnetic field from within its volume. However, certain kinds of superconductors, type 2 superconductors, actually exhibit a slightly different effect if a sufficiently strong magnetic field is present. The magnetic field lines from a permanent magnet can penetrate the superconductor, and they sort of get hung up on impurities. They excite little currents inside the superconductor, and the flux distribution of the magnetic field of all those currents gives you an interaction at a distance that's not the repulsion of the Meissner effect, but is more of a stable interaction. This is important to note. It occurs in high-temperature superconductors like, high temperature being very relative here. Yttrium barium copper oxide is the sort of the poster child for these things, and it does this below a temperature of 88 kelvins. This interaction provides essentially a nonlinear stiffness and damping between the magnet and superconductor. A fairly effective model is to just connect this here's a permanent magnet, here's a piece of YBCO, and they're separated by about 2 centimeters. Just connected by a many degree of freedom spring, many degree of freedom damper there. And this interaction is stable in many degrees of freedom. It's not limited by Earnshaw's theorem, which says that if you want to get a configuration of magnets to hover near one another, you have to use active control. This happens purely because of the this happens purely because of the material properties of the superconductor and the magnet. There's no power being applied anywhere in this or control. And the parameters of this pinning interaction are set by where the magnet is when the superconductor crosses below its critical temperature. Now, what do I mean by that? I'm going to show a picture. I'm a physicist, so I like drawing forces as potential wells and things. This is the potential function between the magnet experiences in its translational degrees of freedom if there's a superconductor here. And the force that the magnet experiences is the negative gradient of this well. So the magnet tends to fall into this well here and it gets stuck right about there. And this is only true if the magnet is first placed there when you cool the superconductor. That's called field cooling the superconductor. And if you field cool the magnet, or field cool the superconductor with the magnet in different locations, for instance, very close to the superconductor, you get a very steep potential well. If you field cool it with the magnet further away, you get a very shallow potential well. But the equilibrium of the well is always wherever you first put the magnet when you cool the superconductor. You can also see here the nonlinearity in the well. It's it's shallower on the direction away from the superconductors and steeper towards the superconductor. Now, I couldn't bring any liquid nitrogen on the airplane with me. I need more than 3 ounces to demonstrate this. So here's a video. We field cool the superconductor, so we put nitrogen in here with the magnet in place, and then I can take away everything supporting the magnet, and it levitates stably in 1G. Now you can see that there's this there's stiffness in many degrees of freedom here, and it's nonlinear stiffness. Right about here, I'm going to bear down on that magnet with just about all my weight, and the magnet never touches the superconductor. That's how strong this interaction is. However, if I try to pick it up, I can get a substantial amount of play there. But there is a stiffness opposing me when I do that. This can be stable, or excuse me, can be stiff in many degrees of freedom. So I can pull the superconductor around, but it's not necessarily stiff in all degrees of freedom. Particularly, it's not stiff in degrees of freedom where the magnet has 0 field gradient. So that magnet can rotate about its axis, since it has a symmetric field about that axis. Also, the flux distribution that's embedded in the superconductor is sort of remembered by the superconductor if you take away the magnet. So you can take it away and then later on bring it in again, and it'll float there right in the same equilibrium. You may have noticed that there's not very much damping here. That's actually a good thing in this case, because damping from flux pinning comes from hysteretic energy losses. So the fact that we have very low damping here goes hand in hand with the fact that this is not a terribly hysteretic system, for this particular superconductor at least.